Okay, let's talk about solar radiation as it travels through the atmosphere. Before we look at how it travels through the atmosphere, let's talk about the solar constant. The solar constant is a number that represents the maximum amount of solar energy received at the top of the Earth atmosphere system for a particular location. And that location would be someplace where the sun is directly overhead. So, for example, right above the equator on the equinox. And the value has been measured to be about 1,367 watts per square meter. The solar constant is useful for us when we model what happens to solar radiation and what amount of energy is going to be left for the Earth atmosphere system. The law of energy conservation says that we need to be able to account for all the energy that comes in. So in this case, we're talking about incoming solar radiation, and I'm going to designate it by this symbol, SW, for shortwave radiation incoming. So it's coming into the Earth atmosphere system from the sun. And if we imagine that the amount of incoming shortwave radiation that's received by the Earth atmosphere system equals 100%, so all of it, then we can use the law of energy conservation to start to account for what happens to that energy as it passes through the atmosphere and reaches the Earth. Some of it is absorbed, some of it is scattered, and some of it is actually transmitted to the Earth's surface. So we'll talk about these different things, and we'll start by talking about scattering. So scattering is the process where solar radiation redirected because of different atmospheric constituents that it encounters. And these constituents can be gases, they can be particles, so the scattering is wavelength dependent. For example, oxygen and nitrogen, which make up most of the gases of the atmosphere, preferentially scatter the blue and violet light that's coming from the sun. So those molecules scatter the blue and violet light, and that produces what we see as the blue sky. That type of scattering, where it's preferential to a particular wavelength, is called Rayleigh scattering. Another type of scattering, which scatters all of the wavelengths equally, is called Mie scattering. It's spelled M-I-E, and it's named after the scientist who discovered it. And Mie scattering is a good example of that is clouds. Clouds appear white to us, and that's because the particles, the water vapor and other particles that make up the cloud, scatter all of the visible light that's coming from the sun equally. So all the different visible light gets scattered, and our eyes record that as white. Some solar radiation that's scattered is backscattered, which is another word for reflected back to space. This concept is embodied by the word albedo, and albedo is the percent of incoming shortwave radiation that's reflected back to space. It's denoted by the Greek letter alpha, and its formula can be read as this. So it's the amount of outgoing shortwave radiation divided by the amount of incoming shortwave radiation, and it's given as a percentage. Albedo is roughly correlated with the color of an object. So the lighter the object's color, the higher its albedo. You can see that in the snow. It has an albedo of anywhere from 80 to 95%, which means that the amount of solar radiation that is received on a snowy surface, the vast majority of it gets reflected right back out. This is something you may have experienced if you've been out in snow, maybe skiing or something, on a sunny day. You can get sunburn on your chin or on places that you're not used to getting sunburn because of all the reflected sunlight. You can see in this diagram the albedos for other surfaces. So grass and green areas have varying albedos. Croplands, which have some earth underneath and some greenery on top, have slightly lower albedos. Blacktop has a very low albedo. It does not reflect a lot, it absorbs a lot, and we know this because when we walk on a blacktop surface in the summer, it's very hot. A lot of the solar radiation is being absorbed. And you can see different roofing and the water. Water bodies have a huge variation in their albedo because the albedo varies with the solar altitude. So getting back to our global solar radiation budget, we can plug in some percentage values to see what percentage of the incoming shortwave radiation is reflected, absorbed, and transmitted to the surface. So these are averages for the whole globe. The amount that's reflected is 30%. So 30% is the albedo of the entire Earth averaged together. The amount of energy that's absorbed by the atmosphere is 23%. And then that leaves 47% to be absorbed by the Earth's surface. And that accounts for all of the incoming solar radiation. So what happens to this energy that makes it to the Earth's surface is that the Earth heats up. And then once the Earth heats, it's able to emit its own energy and what we call long wave energy, as we'll talk about in just a moment. And we can talk about the global radiative equilibrium, which is basically the balance between the amount of incoming energy from the sun compared to the amount of outgoing energy that the Earth atmosphere system emits back out to space. So we have incoming solar radiation from the sun, some of which is reflected back out to space with that 30% albedo we just talked about, but some of which reaches the surface of the Earth or reaches even into the atmosphere. It's absorbed either by the atmosphere or the Earth. We call this the Earth atmosphere system. When it reaches the Earth and is able to heat up the Earth then warms up and is able to emit its own energy. But the energy that the Earth emits, as we've seen, is in the long wave spectrum of the electromagnetic spectrum. So we have this long wave energy that's being emitted by the Earth, and the symbol you see here is LW up. So this is energy that the Earth is emitting up to the atmosphere. And then some of that energy is able to escape from the Earth through the atmosphere right back out to space. But some of this emitted long wave energy from the Earth's surface gets trapped by the atmosphere, and it heats the gases and the things up in the atmosphere. And then from there, the atmosphere can re-emit some of that heat back down to Earth, or the atmosphere itself can emit some of that long wave energy to space, and we get this kind of back and forth play, with some of it coming back to heat up the Earth and some of it going back out to space. This is what we call the greenhouse effect. And we call it the greenhouse effect because it's just like a greenhouse. If you imagine a greenhouse that's made of glass, or it's see-through, which means that it allows incoming solar radiation to pass right through it, just like our atmosphere does. Our atmosphere lets through a lot of incoming solar radiation. So just like the glass in a greenhouse, that energy comes in, heats up the surface inside the greenhouse, and then causes long wave energy to be emitted by the Earth or inside the greenhouse. And the glass in a greenhouse is then impervious to long wave radiation. So whereas it lets solar radiation in and out, it does not allow the long wave energy to get out. So the greenhouse heats up. And this is exactly what happens on the Earth. If it weren't for the Earth's atmosphere, we wouldn't be able to hold on to any of our heat. It would all just escape, and the Earth would not be habitable for life. So the greenhouse effect describes an important component of the atmosphere, which is to warm us up. It's as if we have a blanket on top of the Earth, and it keeps us warm. This image shows outgoing long wave radiation in different wavelengths, broken down by different greenhouse gases. Greenhouse gases are gases that have this effect that I just described. They don't absorb solar radiation, or if they do, it's in small amounts, and they trap long wave radiation. So here we've got the wavelength across the x-axis in micrometers, and on the y-axis absorptivity, which is just a 0 to 1 value, with 0 being not at all absorbing and 1 being completely absorbing. And we can see the whole atmosphere here in the bottom, and then the different components, the different greenhouse gases broken out individually above that. So one of the primary greenhouse gases is water vapor, and you can see that it absorbs infrared energy in many of these different wavelengths. Another greenhouse gas is carbon dioxide, and you can see where it peaks, the places where it absorbs infrared energy. We also have oxygen and ozone up here. Oxygen absorbs a little bit of long-wave energy, and so does ozone. Not much, you can see, but it does absorb some. We also have nitrous oxide, another greenhouse gas, and then finally we have methane. So you can see the effect of each of these individually and then all together. And what happens is we have a few gaps where there's nothing absorbing. And we call these windows. And there's two windows here that are important that are at about 8 and 10 micrometers. These are called infrared windows because there's no greenhouse gases that are absorbing energy at those wavelengths. So it's like opening a window and allowing some of the heat to escape. So we have the naturally occurring greenhouse effect, but what happens if we add more greenhouse gases to our atmosphere? Well, the calendar effect says that we can actually change the climate if that happens. And to test this, we've been monitoring carbon dioxide in the atmosphere since 1957, and we have this famous graph, which you may have seen, that shows the atmospheric concentration of carbon dioxide. So across the x-axis we have time, the years, so it began in 1957 and it continues to this day. And then on the y-axis we have atmospheric CO2 concentration. And you can see that it's increased dramatically. Look at a particular portion of this graph, and over here on the right we see a blow up from the years 2004 to 2011. You see this up and down behavior in the annual readings of carbon dioxide. And what's happening here is that plant matter, vegetation on the earth, absorbs and stores carbon dioxide in its leaves. So each summer, a lot of the atmospheric carbon dioxide is uptaken by vegetative matter. And so we see a low point for that year's reading. And then in the winter, once the trees have dropped their leaves, that carbon dioxide is free to go back up into the atmosphere, and so we see a peak for that year. So does increasing carbon dioxide and other greenhouse gases have an effect on global temperatures? Well, the answer is a resounding yes. And here you see 3 graphs that show the departure from long-term averages of temperatures for land and ocean on the Earth's surface. So at the top you see both land and ocean together, and what we have here is the long-term average, that's the 0 point, so these are representing deviations from this average. And then we can see when it dips down below that line, we have a cooler than average year, and when it dips above that line, or it rises above that line, we have a warmer than average year. So you can see the effect of land and ocean together, and then the individual effects over ocean and land. These effects are always more extreme over land for reasons we'll talk about when we get into temperature. But for now, you can clearly see that the last several years, so from the late 70s onward, we've had increasingly warm temperatures that are far above the normal. So compare that to what was going on in the earlier part of the 1900s and late 1800s. You see that we had below average temperatures. Now they're all above average. So we talked a little bit about the ozone layer in a previous chapter, and remember it's located up in the stratosphere. So we have the troposphere closest to the Earth that goes up to about 10-12 kilometers, and then the stratosphere begins, and the ozone layer is in the lower part of the stratosphere. So the ozone layer receives intense incoming solar radiation, and it's so intense that it's able to break apart oxygen molecules. Oxygen is denoted by O2, and the incoming solar radiation can break those molecules apart into individual oxygen elements. And then we have these individual oxygen elements that can combine with O2 elements to create O3, which is ozone. And this goes on throughout the day, and we have the formation of the ozone layer. So the ozone layer absorbs some of this incoming solar radiation. It particularly is known for absorbing UV radiation. And this is important to us down on Earth because our skin and really all life as we know it, vegetation and animal life, is negatively impacted by ultraviolet radiation. So here's the graphic that shows concentration of ozone. So across the bottom we have ozone concentration and then altitude as we rise up in the atmosphere, kilometers on the left and miles on the right. And you see the ozone layer up here, up in the stratosphere, and the concentration that peaks through what we call the ozone layer. Ozone down here in the troposphere is pollution that's caused from exhaust from cars and factories and whatnot, and its interaction with sunlight. So we get ozone down on the surface, which also absorbs solar radiation and makes things warm and ugly. It's what causes smog. So when you hear ozone, there's two situations. There's the ozone layer, and then there's the ozone that's the tropospheric ozone, that's the pollutant. But our ozone layer is the one that concerns us now because there's a hole in the ozone layer that has been observed over the Antarctic since the late 70s. And this ozone hole is noticed in the southern hemisphere spring, so right at the end of the long southern hemisphere winter. The main cause of this hole is CFCs, chlorinated fluorocarbons, which are chemicals that are used in air conditioning and other industrial purposes. And it's been found that they stick around in the atmosphere. They make their way up into the stratosphere, and they're very persistent, so they stay in the atmosphere. And they interact with the sunlight, and through a series of chemical reactions, they destroy ozone molecules. The Montreal Protocol was an international treaty, an agreement to limit CFC production so that we could stop this destruction of the ozone layer. It would be incredibly detrimental to Earth. And in fact, we've seen detrimental effects. There's been marked increases in skin cancer in humans and animals. Here's a graphic that shows the Antarctic ozone hole from 2006, which was one of the years for which the ozone hole was largest.